Okay, so in this screencast, we're going to try to do an example related to crystallization and try to read this problem and work through it on your own before watching the screen. So in this example, we have a cooling crystallizer. I'll just draw like this, and it's operating at 30 degrees C, and we are feeding a fluid that contains 100 kilograms total, as given in the problem statement. And that contains some mass of water and a mass of salt. And in the crystallizer, we're told that we produce 25 kilograms of the salt, which is KNO3. And then we still have a liquid solution that also exits, and all the water exits there. So we have that same mass of water. And then we have some smaller mass of salt, basically MS minus 25 kilograms in the aqueous solution, and so I'll just call that MSAQ. And the reason, and we know that this should be a saturated amount of salt inside our liquid water, because otherwise we wouldn't have equilibrium between a solid phase and this liquid phase. Right? Saturation implies equilibrium, and we're assuming that we go all the way to equilibrium at 30 degrees C so that we produce both solid and a liquid state in this case. And what we're asked is how many degrees above saturation we have in the feed. So how many degrees of superheat do we have? All right, which we'll get to in just a minute. But first, we basically want to solve for all of these flow rates, and that's going to help us answer that question. All right, so if we do an overall balance, then that's just N equals out because there's no reaction. So we have 100 kilograms total coming in is equal to 25 kilograms of the salt coming out, plus the mass of the water, plus the mass of the salt in the aqueous phase. All right, at saturation, at 30 degrees C, we can look on our table. All right, we're about right here. And of course, there's some error in reading off this plot, but I'm going to assume that that the solubility is 48 grams per 100 grams of water, or in other words, 0.48 grams per gram of water. All right, so then 0.48 is equal to the mass of the salt in the aqueous solution over the mass of water. All right, we can then solve for the mass of salt in the aqueous solution here. It'll be 75 minus MW, and we can plug it into this equation. So now we have one equation and one unknown, and the mass of water turns out to be 51 kilograms, and therefore the mass of salt in the aqueous solution turns out to be 75 minus 51, if we use this top equation here, which is equal to 24 kilograms. And finally, the mass of salt that we must have had in the original solution is therefore 24 plus 25, so we have 24 kilograms of salt in this stream and 25 in this stream, so that means we must have had 49 kilograms here to start off with, to go with our 51 kilograms of water. Now what we're asked is the amount of superheat in the entering solution. So the entering solution is not, you're not given any information that is at equilibrium with any solid phase. All right, so it may be a superheated system that is well above in temperature where you would expect the salting out to occur. And the degrees of superheat is basically the degrees above the saturation condition at the inlet concentration. All right, the inlet concentration, so at the inlet, right, that would be equal to the 49 kilograms that we have of salt over the fact that in our 100 kilograms we have 51 kilograms of water that we determined from our balance. All right, and if we take that ratio, that turns out to be equal to 0.96. All right, and we can look up 0.96, or on this plot, about 96 grams of KNO3 per 100 grams of water. And we see that it approximately, again, it's hard to read this with a high degree of accuracy, but we're at approximately 55 degrees C. Right? So at 55 degrees C, the maximum amount of salt we'd expect to be able to dissolve in our water would be 49 kilograms per 51 kilograms of water. All right, but our inlet solution actually enters at 100 degrees C. All right, and so that means that we're superheated. We could accommodate a lot more salt in the entering solution, right? But we don't have a saturated system in that case. All right, so we are less than half actually the amount of salt that we could accommodate at 100 degrees C. All right, at 55 degrees C we'd be saturated. And so to determine the degrees of superheat, we simply, so I'm going to call this a delta He superheat. All right, then we simply look at our 100 degrees C, which is our inlet temperature, all right, minus the temperature that corresponds to saturation at the conditions here if we were at equilibrium, and that's 55 degrees C. All right, and so we have 45 degrees of superheat. All right, so in this crystallization process, when this enters 100 degrees C, right, the temperature is going to have to fall all the way to 55 degrees C before you start to form any crystals, because above 55 degrees C, we don't expect any kind of equilibrium between the solid and liquid state.